Okay, folks, in this video, we're going to take a break for naming and take a look at some of the properties of organic compounds. We're going to look at things like melting point, boiling point, and whether a molecule is soluble in water. So those are the kind of three key things that we're going to try and describe about every molecule that we look at. And we'll do a little bit about their chemical properties as we go along as well. But for now, this first video is going to just focus on their physical properties. Right? So melting point is important if you want to know if something is a liquid or a solid or a gas at room temperature. And solubility describes how well it dissolves in water. And the opposite of that would be something that dissolves well in a solvent like turpentine or Varsol or ethanol, things that are a little different than water. And we'll go into the explanation between what are called non-polar solvents, things that aren't like water, and polar solvents, things that are like water that do dissolving. Okay, so hopefully those three ideas can come through, and we'll just focus on the type of molecule that we've already been looking at, which is alkanes, alkenes, and alkynes. So we're just going to look at molecules basically that have carbons and hydrogens in their molecules. Now, whenever we look at a molecule, the type of atoms that are in the molecule and the way those atoms are arranged are going to affect the molecule's ability to stay as a solid, a liquid, or a gas, and to dissolve in water. And so the shape of the molecule kind of affects how the molecules can interact with each other. So if the molecules are very kind of shaped with lots of branches and things on it, so if we were to draw like a molecule like an alkane, and then we had all kinds of funny branches and things on it, that makes it difficult for those molecules to get close together, and they have trouble interacting with each other. Or if you have a more straightforward shape, that molecule can interact with another molecule. So let's put another one here. And they can interact with each other very well. And that's important if we're going to make compounds. Because how well the two molecules interact with each other determine whether it's a solid, a liquid, or a gas at room temperature. The other thing that can affect a molecule is the type of atoms. And so we're going to deal first of all just with carbon and hydrogen atoms. But as we move along, we'll add oxygen and nitrogen atoms to our molecules. And they affect the polarity of the molecule. So you may remember we were talking about polarity in the last unit. We did that work with M&Ms, and we saw that the color of the M&M, it would dissolve in the water. So we said it was a polar molecule. But the letter, the M, and the coating on the outside of the M&M was made out of wax, and it would not dissolve in water. So it was a non-polar molecule. So we're going to use that same idea and try and differentiate all of our organic molecules into these two groups. Okay, let's look at alkenes, alkanes, and alkynes, the single bonded, double bonded, and triple bonded molecules, and just see how we can figure out the properties of these molecules. Now, you could go and memorize all of this information that I'm going to give you, but I'm going to try and teach you some ways to think about each molecule so that you can just predict whether or not the molecule will be soluble in water or whether it'll have a high or low boiling point and melting point. Okay? So if you just want to memorize it, then starting from here, all three of those kinds of molecules are all insoluble in water. So things like propane, which was the 3 carbons in a row, does not dissolve in water very well. The only bonds in propane are these CH bonds. And CH bonds are nothing like the bonds that are in a water molecule. CH bonds are non-polar. So they will only dissolve in other things that are non-polar. But if we're trying to dissolve this propane in some water, it's not going to dissolve because water is the kind of at the opposite end of the bonding spectrum. Water is actually polar. So water has an O and an H, and an H. And if you recall our discussions, because the oxygen pulls on the electrons harder than the hydrogen pulls on them, the electrons shift toward the oxygen, making this a little bit negative and a little bit positive. And so these negatives and positives like to stick to one another. And all the water molecules will hold on to each other because they have both positives and negatives inside their one molecule. And if propane comes along to be dissolved in some water, it can't mix in with the water because it can't separate the negatives and positive attractions that are between two water molecules. For instance, if we were to copy this water molecule and then put it down here, we can see that the negative of the oxygen is attracted to the positive of the hydrogen. And the only way that propane can be dissolved would be for it to come in and move in between water molecules. Well, because it's not polar, it can't break this negative and positive attraction that exists between the two water molecules. So propane, methane, acetylene, all the different kinds of compounds we've looked at so far will not really dissolve in water because they can't get inside the between two molecules and kind of break them apart so that it can dissolve. So that doesn't happen with alkanes and alkenes and alkynes. You have to be polar if this is going to happen. And these molecules are non-polar and water is polar. So these two things do not mix. And if you can look at a molecule and see that it's non-polar, then you can always predict whether or not it'll dissolve in water. Okay? The second thing to look at is the melting point and the boiling point of these molecules. And so when we have talking about these numbers, we have to think of like if we have a solid, you have all the molecules packed closely together and they're holding on to each other very strongly. Right? If we have a liquid, say in a beaker, the molecules are still holding on to each other, but they're very spread out and they can move around very easily. And then in a gas, the molecules are extremely far apart and have no trouble moving around. And what we do as we move from solid to liquid to gas is we add heat. And so if we heat it, it becomes a liquid. And if we heat it, it becomes a gas. And that's because as we heat a particle, you might remember this from grade 9 and 10, those particles are always moving. And as you heat them, those particles start to move more and more. And as they move more and more, they break the attractions between the molecules, the things holding the two molecules together, and the molecules separate, moving from a solid to a liquid to a gas. So when we look at molecules to try to decide what's their melting point, the point at which they'll go from a solid to a liquid, or their boiling point, the point at which they'll go from a liquid to a gas, what we really want to look at is how well can they hold on to each other and how much can we heat them up and break those attractions. So how much heat do I have to add to cause the molecules to separate from each other? And we call that the melting point or the boiling point, depending on which kind of change we're looking at. Okay? Now, non-polar molecules only have one kind of force that holds things together. We talked about a little bit of this, but we'll go into some detail here. Non-polar molecules, because they don't have charges on them, it was discovered that they have tiny little forces called London dispersion forces. And that's what holds the molecules together in these non-polar molecules. So if I have a very long chain of carbons, well, not really long, let's make it 5, and I have another long chain of carbons, there's nothing polar on these chains of carbons because they're all just C's and H's. So there's no little positives and little negatives to attract them to each other. But it was found that a force called a London dispersion force does exist between two molecules of an alkane, an alkene, or an alkyne. And these are just little tiny attractions that kind of hold the two molecules close to one another So I say it's almost like static cling, but it's not that strong because there aren't any charges like static cling. Like if a sweater has a sock stuck to it, those are charges holding those two things together. One of your sock is positive and your sweater is negative. But these London dispersion forces, they hold together molecules that are non-polar. So the only thing affecting the melting point and boiling point of things that are non-polar is how many carbon atoms there are. So the more carbon atoms there are, the more the boiling point and the melting point will go up. So the more C's that we put on the ends of our molecules, so we made these even more, you can see then that there's even more chances for these molecules to kind of attract one another with these little dispersion forces and to hold on to each other. And the better they can hold on to each other, the more heat energy it takes to break them. So better forces of attraction, or in nonpolar, so for nonpolar, more LDF, more London dispersion forces, these little attractive forces that hold nonpolar molecules together, means higher boiling point and melting point. Okay, so longer molecules should be more like a solid, and smaller molecules should be more like a gas, and things in the middle will be either soft solids or liquids. Okay, so those are a couple of things about alkenes, alkanes, and alkynes. Let's just take a look at an example here. So for instance, if I had this molecule of methane, so methane is a one carbon with 4 hydrogens, or octane, 8 carbons with 18 hydrogens, and I wanted to think about which one would, well, let's go through all the properties. Solubility, will it dissolve in water? Neither one of these is going to dissolve well in water because they're both non-polar. So this would be a no, this would be a no, and the reason would be these are non-polar and water can only dissolve polar molecules. So because this is a non-polar molecule, it won't dissolve in water. But if we look at its melting point and boiling point, well, we were just saying on the previous screen that non-polar molecules make LDF forces, London dispersion forces, and they get stronger as the number of carbons goes up. So the higher boiling point is going to be the octane because it has 8 carbons in its chain, and the lower boiling point or melting point is going to be methane. Right? And the difference between these is going to be their ability to make London dispersion forces, or little attractions between molecules. So when I add heat and these molecules start shaking, and their shaking gets increased by the addition of heat, the methane molecules will separate and turn into a liquid or a gas much easier than these octane molecules, where I have to add a lot more heat to these in order to get them to shake apart and form a liquid or a gas. So that's how we look at the properties of alkenes, alkanes, and alkynes. We basically look at how long the molecule is, and that'll tell us whether it has a high or low boiling point. Okay, the final thing we'll look at in this video is there's a little bit of a twist about melting points and boiling points. And having a double or a triple bond does affect molecules and how well they have melting points and boiling points. So let's take a look at 2 molecules that you may be familiar with, at least in their biological words. We're going to talk about saturated fats and unsaturated fats. So both of those kinds of molecules are, one is an alkane, saturated fats. They're alkanes, and they only have single bonds in their carbon chains. The other one, unsaturated fats, we'll look at in a minute, they are things that have at least one double bond in their carbon chains. So we often classify the fats that we eat by whether they're saturated or unsaturated, and let's just take a look at what that really means. So saturated fats, when they only have single bonds in their molecules, you can see it makes a nice regular chain, and all of the atoms are kind of in a nice straight line. And so you can imagine that when these molecules are put close together, so let's just make a copy of this molecule, clone it, and then we try and bring them close together, you can see that they could very easily line up and make fairly strong London dispersion forces. So LDF forces are going to be fairly strong in alkanes or in saturated molecules as opposed to those that are in unsaturated molecules. So because it can make very strong, fairly strong London dispersion forces between the two molecules, the length of the chain in these alkanes means that there's lots of LDFs. And so saturated fats, things like butter, are often solids at room temperature. And because they have enough attractions in these long single bonded chains to hold on to each other, and they form a solid at room temperature. The other thing that we'll come back to later on, but we'll mention it now, is that because saturated fatty acids only have single bonds in them, single bonds are very, very strong. And so from a health perspective, these molecules are very stable and they don't react very easily in your body. Your body has a hard time using them because of their stability and how hard they are to make react. And so that's one of the reasons saturated fats is bad for you, is that they can build up in your body and then lead to long-term health problems if you have too many saturated fats. Now, just to make that make a little more sense, if we compare it to this acid, and so this is a fat that is an unsaturated molecule, and it's unsaturated because right here it has a double bond. And you can see instead of being that nice long chain that we just saw, the double bond makes little kinks or makes bends in the molecule. And so now you can see if I tried to line up two molecules, this bend in the molecule would prevent a second molecule from getting very close. So because of that bend kind of prevents me from lining up all of the carbons in a very good way, that means that there are less chances for LDF. So these bends lower the amount of LDF, London dispersion forces. And if you lower the amount of London dispersion forces, you lower the melting point and you lower the boiling point. So alkenes, like this one, which are also called unsaturated fats in the molecule that I've drawn, they have a double bond in them, which makes their shape, changes their shape in such a way that they don't stick well to each other. And if they don't stick well to each other, these are actually liquids at room temperature. So this would be something more like olive oil, which is a healthier oil for you, but it's a liquid at room temperature. It's not a solid. And from the biological point of view, we're going to take a little look later on that double bonds are actually weaker than single bonds. They're easier to break. So if we add a double bond to a molecule, it makes that molecule more reactive, and your body has an easier time metabolizing it. So that's one of the reasons that unsaturated fats are better for you. It's better to have unsaturated fat in your diet than saturated fat. And the only difference between this molecule and this molecule is the presence of a double bond. And that changes it from being a solid at room temperature to being a liquid at room temperature. It takes a molecule that is not very healthy for us, and if it has double bonds in it, it becomes a healthier fat molecule for us. So just by changing that one little bond in an atom changes all of those properties about these two fatty acids. But in general, you can say that about any alkane versus any alkene. The kene part, the double bond, is going to make it more than likely it's going to make it have a lower melting point and a lower boiling point because it can't make attractions between itself and other molecules. Okay, so I think we'll leave that one there. We'll come back and I'll do another video on oxygen and show you what the effects of oxygen are. And then you'll have kind of the whole story of how we predict melting point, boiling point, and solubility. And then we'll look at a few more molecules and learn how to name them and how to draw them. And well, that'll be pretty much be the unit. So hopefully you're getting onto the naming. If not, please ask. And for now, we'll leave it there. Thanks.